everyone. Welcome to Data Platform Summit 2020 and welcome to this session. The title of today's session is Building a Custom SQL Server on Containers Image for Deployment. Now, there's actually a little bit of a play on words in the title because, well, this is more than just deploying SQL Server. Because anybody who knows how to work with SQL Server can deploy SQL Server. Might take them hours or days or weeks or months, but that's not the goal. You want to build, number one, a custom SQL Server containers image, one that meets your organizational needs, and not just deploy it. You want to deploy it faster, right? You don't want to be waiting for weeks just to deploy a SQL Server database, okay? You want to be able to deploy a SQL Server database faster. My name is Edwin Sarmiento. I'm a Microsoft Certified Master for SQL Server and a former Microsoft Data Platform MVP. This session is a snippet off of a chapter that I wrote in the book, The SQL Server DBA's Guide to Docker Containers. Before I move on to the presentation, I'm going to make two main assumptions. Number one, you should at least have a little bit of an understanding of how Docker containers work, like how Docker runs containers. Not too deep, just a little bit of understanding. And the second assumption, which I think is even more important, is that you should have years of experience working with SQL Server. This is not a beginner session or an introductory session. This is more for intermediate to advanced session. That's why I'm making these assumptions. All right, so let's move forward. I want to start off with defining a term that has been overly used but totally misunderstood. The term is DevOps. People are dropping the term DevOps. They're putting it on their resume, but they're really not understanding what it is. I took this definition off of AWS because it really gives you a frame of how to approach your development practice and operational practices from a DevOps perspective. And I've highlighted key phrases and words to emphasize what it really is. It's a combination of cultural philosophies, principles, practices, and tools. It's not one or the other. It's the combination of all four. But what's the goal? The goal is to increase an organization's ability to deliver applications and services at high velocity, aka faster. Okay. I remember the days when I was still working as a data center engineer. We've been doing DevOps even before everybody started calling it DevOps. And it's not just knowing how to use the tools. It's not just knowing how to automate things. It is a combination of all of these four things. In fact, I barely even touched my keyboard when I was working as a data center engineer. I spent so much time on a whiteboard, writing workflows on a piece of paper, outlining the processes before I even write a single line of script. And the reason for that is we want to make sure that we're delivering our services faster. One mistake is all it takes to take an entire data center, and that is a catastrophic thing, especially if you're dealing with a global data center that's spread across different countries. And so part of our practice is not just to automate majority of the things that we do. We are also very particular about the people that we hire, meaning you don't just hire anybody. We hire people who have this way of thinking around automation and way of thinking around how to do things. Part of the interview process is looking for for experiences on how they've managed to improve operational efficiency. Why? Like I said, we want to minimize human error. And so if your way of thinking is, I'm just going to go click and drag and, type, that doesn't work for us. Okay. And so part of that is, again, we built this culture around the team in such a way that every single member of the team would have this way of thinking. The Unix admins, the DBAs, the sysadmins, the network engineers, the developers, every single one of us had this way of thinking. It's also beyond the tools that we use. The tools is just one aspect. It's how we do what we do with the people that we do it. There's another definition that I wanted to point out. It's evolving and improving products or services included at a faster pace than organizations using traditional software development and infrastructure management processes. The idea, again, behind this is you want to be able to provide products and services faster. And of course, I'm generalizing the term products because they could be digital products, right? And services. They could be digital services. You want to make sure that you are providing new features and new products faster because the market is moving fast. And if you can't adapt with the fast-moving market, the business does not survive. That's why this is very important. Okay, I want to point out some of the things that were challenges from way back when. Enter the days of physical machines. And I'm going to use SQL Server as an example because that's exactly what the topic is all about. How long did it take for you to deploy a SQL Server database in the days of physical machines? That depends. Might take weeks, months even. Why? Before you can even install SQL Server, you would have to tell your purchasing department. Your purchasing department will then place an order to the hardware vendor, and the hardware vendor will then deliver the hardware to your data center, rack and stack it, configure connectivity before you can even install SQL Server. Did I say weeks? I've had experiences where it took months to install SQL Server. There are two challenges with physical machines. Number one, it really did take long to deploy SQL Server on physical machines. And I mean long, weeks, months even. The second challenge was, we call ourselves data professionals, right? The second challenge was the fact that we were guessing. What do I mean by that? Well, if you're deploying a new SQL Server instance, no performance baseline whatsoever, and your boss says, well, how much memory, CPU, and storage resources do we need for this? Exactly. You don't know. Why? Because you don't have the metrics that you can use so you can purchase the right hardware. So you end up buying the most powerful, the most expensive machine. And, 6 months, a year down the road, your server is barely hitting 40% utilization. Your CIO walks over and say, hey, we're not maximizing our investment right there. And so those are two challenges. How do we address those two challenges that existed with physical machines? Enter virtual machines. Virtual machines solved those two major challenges. Want to deploy SQL Server? Sure. Create a VM, install an OS, install SQL Server. Could take a couple of hours, but not a couple of weeks, right? So it addresses one of those two challenges that I mentioned. The second challenge is, now your server is no longer sitting at 40% utilization. You can, run as many virtual machines as you possibly can on that physical machine. And, we've even had this term called over-provisioning. We've provisioned so much virtual machine on a physical host that now virtual machines are now suffering as far as performance is concerned. But don't get me wrong, the virtual machines solve those two major challenges that existed in the physical machine days. What about containers? What is a container? Because every technology should solve a major business problem. Virtual machines solve those two challenges that I mentioned. What about containers? What problem does a container solve? It is to reliably run software when moved from one computing environment to another. I mean, just think of the idea behind upgrading SQL Server. I want to upgrade SQL Server from 2008 to 2016. Well, you're doing both an upgrade and migration, which means, well, I have to make sure that I have enough compute resources. Well, not only that, I have to make sure that SQL Server still runs the way I expect it to on a new version. What about your developers creating a stored procedure on their environment, deployed it in production, say, hey, it worked in my laptop, but then you're experiencing production, rapid performance issues in production. Not only that, some tweaks, some configuration settings on the development environment don't look exactly like what's happening in production. Even with proper change management process, you cannot guarantee that your development environment would look exactly like your production environment. Or what about this? What about moving from one platform to another, like physical to virtual? Sure, your hypervisor would have tools to do a P2V or a physical to virtual migration. But what about physical to cloud? Does your cloud provider have the tools to do a P2C? Or what about V2C from VMware, for example, to Microsoft Azure? Sure, Microsoft may have tools, but then, how would it work? Would there be limitations? Are there features that won't work because now the VM is running on the cloud? So these challenges are some of the things that containers try to solve. Like I said, the technology is only useful if it solves a major business problem. Okay. Now, most people interchange containers and VMs. Like they kind of mix and match the two and refer one term with another. I want to differentiate containers from VMs. Because a lot of people think, well, containers are actually virtualization 2.0. Well, they may be right, but what is it really? So let's define what these two technologies are. Let's start with the virtualization platform. If you have a VM environment, you're probably aware of this, but virtualization leverages abstracting the physical hardware. Okay, so let's start off with your hardware, your physical hardware. You got your CPU, your memory, your disk, your network, and then you install a thin layer of abstraction, which is your hypervisor, your Citrix, your VMware, your Hyper-V. And then on top of the hypervisor, you create a virtual machine. Now that virtual machine, like I said, abstracts the underlying physical hardware. You assign a virtual CPU. You assign a virtual RAM, a virtual network adapter, a virtual disk. But that's not enough. You won't be able to install an application on that VM unless you install an operating system. Every single VM would have its own operating system. Only after installing an operating system will you be able to install an app. By the way, I'm going to start calling SQL Server an app from this point on. The number of virtual machines that you can run on top of a physical machine will depend, of course, on the resource consumption of those virtual machines. On the other hand, containers abstract the operating system. So let's have a look at this. We'll still start with your underlying physical hardware, but instead of creating a hypervisor layer, we're just going to do what we've done in the past, install an operating system. Your operating system can have the capability to run containers. With Windows, it's just a feature that you install. With Linux, it's a package that you install. And then you can create a container. Now, like I said, with virtualization, you're abstracting the physical hardware. With containers, you're abstracting the operating system, which means unlike a virtual machine, where you have multiple copies of the operating system, with containers, you only have one copy of the operating system. Containers allow you to install an app on top of the container. Why? Because again, it's abstracting the OS. So no need to install an operating system on a container, right? And you can have as many containers as you possibly can, depending on the amount of resources that you can run on that physical machine. Now, just from a storage perspective, look at these two. Look at the difference between virtualization and containers. With virtualization, your VMs are bigger in size as far as file size is concerned, because, well, let's just look at Windows. You got the VM, you got the operating system, you got everything else, and then you have the app. Versus on a container, you don't have a copy of the operating system inside a container. It's abstracting the operating system. It makes the operating system look as if it exists in its own space inside a container. That's why you can install an app on top of a container. Those are the two different things, okay? But the main thing is virtualization abstracts the physical hardware. Containers abstract the operating system. And that's also one of the reasons why people call containers virtualization 2.0, because really there is some form of virtualization. But instead of virtualizing the hardware, you're virtualizing the OS. Containers are actually a Linux concept. It was taken from way back the late 1970s from a Unix concept. It was developed late or after 2010 and commercialized it, having been from a Linux concept. Most of the examples in the demos that I'm going to be showing you will be based on a Linux operating system. That's why you really need to be very comfortable with command line and scripting. Okay? Containers virtualize the underlying operating system. And I'm not just talking about Linux here. It could be Windows. Okay? Because it's abstracting the operating system kernel, the container and the operating system should share the same kernel. Meaning, I can't run a Windows container on a Linux host, and vice versa. I can't run a Linux container on a Windows host because they have two different operating system kernels. Now, let's look at the Windows thing. For example, I can't run a Windows Server 2019 container on a Windows Server 2016 container host. Okay? But I can run a Windows Server 2016 container on a Windows Server 2016 host. Because again, containers virtualize the operating system kernel. They share the host's kernel. And because they share the operating system kernel, or rather the operating system of the host, they can access resources that are available from the operating system level. In fact, this is where the concept of resource control come in. Imagine a container as if it was a process running within an operating system. Something happens to the process, any other processes running in the operating system would not be affected. You can kill a process without affecting the other processes. The process might have a memory leak, but it would only affect that process. Of course, you really have to restrict the resource consumption of that particular process. And that's what allows containers to. That's what allows you to run multiple containers in the same operating system. And like I said, they may feel like lightweight virtual machines, but they're not virtual machines. They do abstract the operating system, much like virtual machines abstract the physical hardware. But again, they're not virtual machines. Okay. How does Docker run containers? I want to show you visually how Docker run containers. Let's say you have your Docker client and it communicates to the Docker daemon. Daemon is just a Linux way of referring to a background process, just like a Windows service. The Docker client sends a command to the Docker daemon. The Docker daemon would then parse and interpret that command. In this case, the command is Docker run, meaning the client wants to run a container. The first thing that the Docker daemon would do is parse the command, and then in this case, because the client wants to run a container, the daemon will then look at the local disk subsystem. Do you have a copy of the image that this client wants to run? If not, the first thing it needs to do is reach out to a public container registry, and by default, that's the Docker Hub. The Docker Hub contains all, well, not all, but majority of the publicly available images. Think Apple App Store or Google Play Store. The Docker Hub will then respond to the Docker daemon, and the Docker daemon will pass the name of the image. The Docker Hub will then give that copy of the image to the Docker daemon, and the Docker daemon will then pull that image to its local disk repository. Once that image is in the local disk repository, that's the only time that the Docker daemon will run the container that the client was requesting. And then you can run the container from that image. Of course, succeeding runs to create a new container based off of that image won't take as long because the copy of the images were already on local disk subsystem. So you can run as many containers as you possibly want. Of course, with the assumption that the physical hardware can meet those resource requirements that those containers have. I want to show you how this works in environment, and I'm going to be using a Linux Docker host, illustrating how Docker runs containers. So let's go to our demo environment real quick to illustrate how this works. Now, in this demo, I'm going to show you how Docker runs containers in a Linux Docker host. What you've seen in the previous slide is just an illustration of how it works visually. Let's see it in action. I'm currently running a CentOS Linux 7 as my Linux Docker host. I'm using CentOS mainly because this is Red Hat Enterprise Linux's community edition. I don't want to pay Red Hat for the expensive subscription and enterprise support if I'm only doing testing. I've had several customers who are running CentOS in production. Don't do it. Not recommended. I'm not saying you should. But for the purposes of you testing stuff, it's okay. This, again, is the community version of Red Hat Enterprise Linux. Looks and smells like Red Hat without the price tag of enterprise support and subscription. I want to show you real quick, again, how Docker runs containers. I want to run a container using the Docker run command. Now, any programming language would have their own version of Hello World. Docker is no different. So I'm going to run Docker's version of Hello World. And this would explain what I showed you in the previous slide. And what we're going to do is we're going to analyze every line output from this command. Okay, let's start from the first line. First line, unable to find image hello-world latest locally. Remember what I mentioned in the previous slide. We're running a command from the Docker client. In this case, the Docker client is us connecting using the terminal, and it is executing a command to the Docker daemon. In this case, the command is docker run. You're telling the Docker daemon to run a container based on the hello-world image. In fact, if you look at step number 1 here, that's exactly what it's doing. Step number 2, the Docker daemon pulled the hello world image from the Docker hub. Now, like what we mentioned in the previous slide, the first thing that the Docker daemon would do after evaluating the command is check, hey, you're trying to run a container from this image. The image does not exist locally, meaning its own local repository or the local disk. That's why it displays that message, unable to find image. The second line, latest, pulling from a library /hello-world. This is the Docker daemon attempting to contact a public container registry, in this case, the Docker hub. Searches the Docker hub for the hello-world image, pulled down that image, it's a fancy way of saying download, downloads the image to the local repository, meaning the local disk, and then step number 3 kicks in. The Docker daemon created a new container from that image, which runs the executable that produces the output you're currently reading. Hence, why after pulling, see that 12-character GUID value, which was truncated, pull complete. This is when the image has been fully downloaded on the local repository, and then step number 3 kicks in and runs the container. Step number 4, the Docker daemon streamed that output to the Docker client, which sent it to your terminal. Now, here's the thing, though. I want to emphasize step number 2. This is when the Docker daemon reached out to the available public container registry, which by default is Docker Hub, which means your Docker daemon or your Docker host should have access to the public internet. This is so it can reach out to whatever public container registry that you want to contact. Again, the default is Docker Hub. For some of the Microsoft images, you may want to use the Microsoft Container Registry or still use the Docker Hub for some of those images. Again, make sure that your Linux or your Windows Docker host has access to the public internet. If that is a problem for you because of security policies, you can pull the image from one machine and then copy it over to your Docker host. That way you don't have to pull those images from the public container registry. Now, if I attempt to run the exact same command, docker run hello world, it no longer has to pull the image from the public container registry because it's already in the local disk. All it will do is just run a container based on that image. And this is how Docker runs containers. Now, of course, we're SQL Server professionals. We don't want to see hello world. We want to see how Docker runs a SQL Server container. I've already pulled the SQL Server on Linux container image in my local repository. I actually have 2 versions of the SQL Server on Linux image. One is, well, they're both SQL Server 2017 on Linux. One has CU14 and the other has CU18. Okay, I pulled those images because I don't want to waste your time while I pull the entire image off of the Microsoft Container Registry. I've also pulled some images here like the CentOS 7.6.1810 and Ubuntu 16.04. I'm going to use these 2 images later to build my own custom SQL Server on Linux image that we're going to be using in our examples. Let's run a SQL Server on Linux container based on, I'm going to use the CU14 one. And I'm going to use this command. I'm just going to explain a few parameters here. First, -e. -e passes environment variables to the Docker run command. Of course, we're all familiar with the accept EULA parameter because everybody reads the end user license agreement. Says no one ever. SA_password is our sysadmin password, or the SA password. This is the one that we're going to use to log into our SQL Server on Linux instance. -p, we are exposing port 1433 on the host and mapping it to port 1433 on the container. That's how we need to, that's how we are going to connect to container running on the host. So it's port mapping. -name. I want to name my container because I want to make sure that I know exactly what I'm referring to. Otherwise, the Docker daemon will assign a fancy name for the container. I don't want that. For administrative purposes, I want to name my containers. -d, I want to run my container in detached mode, meaning I want to run it in the background, just like a SQL Server service or background process. -h, I want to name this container's hostname Linux SQL 01. Well, sometimes, connection strings that developers write hard code, either the IP address or the hostname. I want to make sure that I'm not breaking any application. And then I want to run this container based off of this image, the mcr.microsoft.com/server:2017-cu14-ubuntu. This is the image that I want to run my SQL Server on Linux container from. The name of the image represents how the image looks like. And we're going to go into more detail with this later when we start building our own container. It's just the fact that when you start naming your containers, or rather your images, you want to make sure that you name them appropriately so that when somebody looks at it, they know exactly what it is. In this case, we can see from here, it's SQL Server 2017 with CU14 running on Ubuntu Linux. And it's not coming from the Docker Hub. It's coming from the Microsoft Container Registry. Okay, let's run this container. And because I already have the SQL Server on Ubuntu Linux, in this case 2017 with CU14 image locally, the Docker daemon will no longer pull the image from the Microsoft Container Registry because it's already here. It will just run a new container based on this image. I just want you to really think about this. I know I did say we want to deploy SQL Server on containers faster. Go back to those days when you were deploying SQL Server, whether it's on a physical machine or virtual machine. Think back to those days. How long does it take to deploy a SQL Server database back then? Go back to the days of physical machines. You have to wait for your purchasing department to place that order for an expensive hardware from HP, from Lenovo, from Dell. You wait for that. So roughly around, a week. And then you install SQL Server. Couple of hours, right? What about in the virtual machine days? If you have a golden image, probably, a couple of hours. With containers, look, I haven't done anything yet. I just copied the image, or rather the command in a terminal. I haven't even run the command. Deploying a SQL Server on container is as quick as 1, 2, 3. And the minute you see that, GUID value, the container is already running. Let's check. And there it is. The container has been running for 8 seconds now. And of course, I can't connect to this just yet. Why? Because, let's see, I named it SQL-Linux on a 1 because it's going through the upgrade process. Yes, every SQL Server image would come off of the RTM version, and then Microsoft will just update it. And that's why you see this database running the upgrade step. It's no different from you installing a service pack or upgrading from a lower version to a higher version. Now that we see the message recovery is complete, we can now connect to it. Let's try and connect to the SQL Server container using SQL Server Management Studio. First, I'm going to copy the password that I used to connect to, to build this image or container rather. And connect to it using SQL Server Management Studio. The IP address for my Linux image is, or my Linux host is this. 228. Okay. And connect to it. And there you have it. We're now connected to our SQL Server on Linux container. Now, remember what I said earlier about running a CentOS Linux as my Linux Docker host? Let's see our container. Our server name is Linux SQL 01. This is based off of the -h parameter that I passed when I ran the docker run command. Let's extend this. And keep in mind, we ran our SQL Server on Linux container based on a SQL Server 2017 with CU14 running on Ubuntu Linux. Oh, wait a second. I thought you said you were running a CentOS Linux for your Docker host. Yes, but keep in mind, though, that because the image is based off a Linux distribution, and the container is simply abstracting the operating system, doesn't matter what flavor of Linux that you're running for your Docker host, so long as they have the same Linux kernel. Like every Linux distribution shares the same Linux kernel. It's just the differences between the implementation of the distribution that differs. Now, in this case, like I said, I may be running a CentOS 7 as my Linux Docker host, but my container is running on Ubuntu 16.04. Okay. So, we now have a running SQL Server on Linux container in our Linux Docker host. And, just by looking at the SQL Server Management Studio, it's the SQL Server we know and like running on a Linux operating system. Well, in this case, it's on a container, but it's running on a Linux operating system. Let me disconnect from here because we're going to be using the same parameters later on to create new containers as we move along. But the point here is we were able to create a SQL Server on Linux container based on Microsoft's publicly available images for SQL Server. Now, I may have been interchanging the terms images and containers, but I want to differentiate one from the other. Because when you start creating your own custom images, you need to know the difference between what an image is and what a container is. And what is an image? An image is a read-only template for creating application containers, whereas a container is a runtime instance of an image. I like to think of this as, let's say, we'll use the analogy from the world of virtualization. You can think of an image as the golden VM image. Let's say you want to create a virtual machine template for all of the Windows servers in your environment. So you would install Windows, you would install the cumulative updates, you make some modifications, maybe you disable the Windows firewall or install an antivirus software or apply group policy objects. And then Once you're ready, you sysprep the VM and then mark it as read-only. Every time you're creating a new VM, based on that template, you can just create a copy of it or a clone of it. The VM template is your image. The new VM, based on that VM image, is your container. Now, you can look at this also from an object-oriented programming analogy, where your image is a class, whereas a container is an object. You can create an object based on a class, and you can modify the properties, the methods, and events of a new object and not make modification to the class. Now, similarly, you can create multiple objects based on that class, and each object could have different properties, methods, and events based off of that class. So those are the two differences. What is an image? An image is a set of files structured in a file system layer. Now, I look at an image just like Lego bricks. Each Lego brick can be used to create different Lego sets. So, for instance, you want to create the you want to make a I don't know, Star Wars maybe, and you want to create a Star Wars Lego set. You can take any Lego brick, so long as, of course, they would fit the Star Wars kit, and you can use that to build your Star Wars Lego set. What you need would be the different Lego pieces and an instruction manual. Now, I can take the exact same Lego pieces and maybe create my Batman Lego set. The only thing that would be different would be the instruction manual. Think of an image as these Lego pieces. Every single Lego piece would contain, files that what your application will be using, maybe changes to the operating system, maybe configuration files, maybe metadata, and every single one of these file system layers with the instruction manual, which is the image metadata, would form the Docker image. The metadata or the instruction manual describes how the image would look like based on these different file system layers, or as I call them, different Lego pieces. I want to show you this image from pulling a Docker image off of the Docker Hub. If you look at the output, you have the pull complete statements. Each line consists of a 12-character GUID value. Actually, those are shortened GUID values, but each of those represent a file system layer. I'm going back to the virtualization analogy. So let's say you want to build a SQL Server 2017 with CU21 or 20, for instance. Imagine every single one of those pull complete statements are file system layers that form the entire image. So let's say the first file system layer would be the virtual machine definition. The second file system layer would be installing Windows, let's say Windows Server 2016. The third file system layer may be for adding some configuration files. The fourth file system layer might be to install security updates for Windows. The next file system layer would be for configuring group policies within the machine. The next one would probably be for installing SQL Server. The next one rather would be for installing SQL Server cumulative updates, and so on, right? Every single one of those file system layers consists deltas or changes from the base image or the base file system layer. So let's say, for instance, I want to create a SQL Server 2017 with CU20, like what I mentioned. I could start off with a SQL Server 2017 RTM image. And every time I would install a cumulative update, I would just create a new file system layer and another file system layer. Okay. Now, this series of file system layers stacked on top of each other are then built using a metadata or the instruction manual, like what I referred to for building a Lego set. And this will be marked as read-only. Can't change it, you can't modify it. This will be the basis of all containers that you will be creating. When you run a container based on an image, what Docker does is it creates a file system layer on top of the existing image. This file system layer will be read-write. Keep in mind, the base image can't do anything about it. It's read-only. The container, read-write. Now imagine for a second you want to create a new user database. The user database would have, data, inserts, updates, and deletes. But then, how do we actually modify the data if the base image is read-only? The changes that you're doing to the image using the container will be written on the read-write layer. Add a new record gets written on the read-write layer. Delete a record gets written on the read-write layer. This will create a view of the image with all the modifications written on the read-write layer. And that's why you can create as many containers as you want based on the image and not modify the image itself. Now, if you want to modify the image, let's say you want to update it. Like I said, you're moving from, let's say, SQL Server 2017 with CU20, you want to move to CU21. You can either create a container, update the container, and merge the changes to the base image, or just create a new one. Create a new image with CU21, and then use that for building containers running SQL Server 2017 with CU21. Now that we have an understanding of the differences between an image and a container, let's start by looking at creating custom images. Now, why would you want to do this? Well, for one, you may not want the images that are provided publicly. Microsoft created these SQL Server on container images, and they're making it available to you publicly. Their public images are running on Ubuntu 16.04, and, well, it's just me. I have preference over Red Hat Enterprise Linux or CentOS. And maybe you want to change the underlying operating system that your container would run on. And because CentOS and Ubuntu share the same Linux operating system kernel, it doesn't really matter. This is where you create your custom image. Typically, they call it containerizing an application because, like I said, we started referring to SQL Server as an application. The way you do this is by using a Docker file. The Docker file is simply an instruction manual for building. Okay? For building. The one that we referred to earlier is an instruction manual for combining the different file systems for building an image. So let's look at what a Docker file is. It's really just a text document that contains all the commands a user would run on the command line to create a custom image. Think of it this way. If you're doing something and you're running commands on a command line, you could write those commands in a text file. And then you run the text file to do all of the commands. In this case, the text file happens to be a Docker file. The thing about the Docker file, though, it's very particular about the naming convention. One, it has to be uppercase D, Docker file, no file extension. Otherwise, it won't work. Has to be uppercase D, so Docker file with uppercase D with no file extension. Okay. This is kind of like the recipe. When you're building your custom image, you're writing the instructions on this particular text file. And then when you build a custom image, Docker daemon will parse this text file and build the image based on the instructions that you wrote on the Docker file. Let's have a look at a very simple Docker file. This one is for creating a custom SQL Server on Linux image, but instead of using Ubuntu 16.04, I'm going to be using CentOS. The Docker file consists of multiple instructions. What you're seeing here is the first instruction in a Docker file, the from instruction. This tells me which operating system I want this container to run on. Now keep in mind, we're not installing an operating system. We're just telling the Docker daemon, hey, when you build this image, I want this image to use this specific operating system. The difference between the Linux Docker hosted operating system and the one that you want to run on top of that Docker host will be the files stored in this particular file system layer. So that's the from instruction. Next is the label instruction. The label instruction is simply a list of metadata that describes your Docker image. And of course, nobody likes writing documentation. Of course, if we can avoid writing documentation, we would. But this is just additional metadata so that you could tell the user of the image what the name of this this image is, what version, what operating system, what environment, and whoever the maintainer is. Because I want to have somebody to reach out to in case I need some help with this image. And you can come up with different name value pair in the label. Again, this is not required. I just like doing it so that I can provide more information to whoever's going to use this image in the future. Next, we have two run instructions. And run instructions are simply commands that you run on the command line. We have two here. The first one is the curl command. This command would simply pull the repo file that describes where SQL Server 2017 can be found so that the underlying operating system can download and later on install it. So the first run instruction is simply pulling the repo file from the Microsoft package repository and then storing it in the local file system. The second run command simply installs the SQL Server on Linux package on this operating system. The -y parameter there is simply to answer yes to all the prompts in the installation. If you've installed SQL Server on Linux before, these two lines might look familiar because these are the two lines that you will run to install SQL Server on Linux. The next line, env instruction, tells the Docker file, or rather tells the Docker daemon that whatever command that you would run within the Docker file, starting from this point, will all run from this environment path. Think of this as an environment variable. In this case, the path gives us the default directory for running SQL Server on Linux, like opt/msql/bin. We have two additional run commands. First one, mkdir. I want to create a new directory named var opt/msql data, which is the default directory for my SQL Server data files. And then the next run command is chmod. I want to modify group and user permissions for the var opt MS SQL and the etc password directories inside this container. The next instruction, the expose instruction, just tells the user that this application will listen on port 1433, of course, SQL Server's default port number. Finally, the last instruction, the CMD instruction. This will run the SQL Server executable, or in this case, the SQL Server binary, because it's in Linux. It's just like calling SQL Server.exe on Windows. The last instruction in the Docker file should be the command that will run your application. And the application needs to be running all the time. Otherwise, if the application stops, the container terminates, and therefore you don't have an application. That's why in this case, the last instruction is to run the SQL Server executable or the SQL Server binary inside a container. It's just like saying, run the SQL Server service. This is how your Docker file would look like when you want to build a SQL Server on Linux image based on CentOS 7.6.1810. Now you can use a Red Hat Enterprise Linux image as well. Just change the from instruction. Like I said, the first two run instructions that you see there are the same commands that you would run if you want to install SQL Server on Linux, particularly Red Hat or CentOS. If you want to see an example Docker file for creating or building a custom SQL Server on Ubuntu image, here it is. There are additional instructions in there because these are specific to installing SQL Server on Ubuntu, but anything after, or rather from the install MS SQL-server onwards, they look the same, right? But the run instructions after the label instructions are very specific to installing SQL Server on Ubuntu. In fact, like I said, the run instructions that you would see there are the exact run or commands that you would run for installing SQL Server on Ubuntu. I'm not really going to use a Windows container because if you look at all the instructions on the Microsoft documentation, almost all of them are for SQL Server on Linux, but it's already here. So I just want to show you real quick how a Docker file looks like for building a SQL Server on Windows custom image. From instruction tells me what base operating system I want to use to run this image on. The next run instruction there, or the run instruction, will create a new directory. Now, unlike SQL Server on Linux, the way we install SQL Server on Windows, we need to make sure that we have access to the installation media. We can't just download it, store it, although we can, but then you need to know exactly where you're pulling from. We don't have a repo file here like what you have with SQL Server on Linux. So here, I'm copying the installation media to a folder inside a container named SQL 2006 dev_sp2. And then from my source, I would copy the entire installation folder to this new directory that I create inside a container. The next run command there looks pretty familiar. If you've installed SQL Server on the command line, this is how you may have done it in the past. Setup.exe and all the parameters through it. The next run instruction will just start, or rather set the startup type of the SQL Server service to automatic. The next run instruction, I just want to delete the installation media because I don't really need it after I've installed SQL Server on Windows. The next one, this is just a trap for running the start.ps1 instruction just below that. And what's kind of interesting with this is, unlike with SQL Server on Linux, I just need to run the SQL Server.exe, or not exe, but the SQL Server binary. and then the container will just run. Here, because you're starting a service, what happens when you start a service? Well, you start a service, command successful, and then it exits. You don't want that. You want to make sure that the container keeps running. That's why Microsoft provided a PowerShell script named start.ps1. And this PowerShell script is simply just, going on an infinite loop so that the container doesn't exit. The last instruction, CMD instruction, will start the PowerShell script start.ps1, passing the parameter values that we provided here. The SA password, the accept EULA, and all the other parameters in here. Like I said, I only showed you this as an example, but I'm not going to show you how to build a custom SQL server on Windows Docker image, because the way I look at it, Microsoft is focusing more on running SQL Server on Linux in a Docker container, not necessarily a SQL Server on Windows on a Docker container. Once you have that Docker file, save that Docker file on the Linux Docker host, and then you run the Docker build command. The Docker build command will parse the Docker file, and using the -t parameter, which is the tag, we'll name our image SQL 2017 CentOS tag 1.0. So every time I want to create a new container based on this image, I'll just refer to the image using the image name with a tag. The dot there is simply a relative path, meaning if I'm going to run the Docker build command, it has to be in the exact same location as the Docker file. Now, you could use an absolute path if you want, but just make sure that if you are running the Docker build command, you will be able to access the Docker file. Like in this case, if I simply use a dot, I'm assuming that I'm going to be running the Docker build command in the same location as the Docker file. Let's head over to our demo environment so I could show you how you can build a custom SQL Server on Linux image using a Docker file. Now, every image that you pull from public repositories will have a list of instructions that created these, and these are all based on the Docker files. First, let's explore. What are these instructions? I don't have a copy of the Docker file that Microsoft used for building some of their images, but there's a way to explore how these images were created. First, let's pick one. Let's pick the SQL Server 2017 with CU14 image. We'll use the Docker history command. We're going to pick, we're going to pick this, and then we're going to use the SQL Server 2017 with CU14 image. And if you look at the different commands or the created by column, looks similar to the instructions we saw on the Docker file. But of course, Microsoft had their own magic in building this. If you notice, you have the CMD instruction, the copy instruction, the expose instruction, label, and so on and so forth. What we're going to do is we're going to build our own custom SQL Server on Linux image. I don't really have anything against Ubuntu. I just don't like using Ubuntu for my container deployments. I'd rather use Red Hat Enterprise Linux, or in this case, I'm going to be using CentOS. But I'm going to show you the Docker file that we can use for building our SQL Server on CentOS. So let's explore some of these. I have in my personal directory inside the Linux Docker host a directory named Docker build. So I want to navigate to that. I also have two directories in here, one for CentOS and one for Ubuntu. And inside this is a file named Dockerfile, exactly how I've described it in the slide. If you look at the contents of the Docker file, it's basically what you saw on the slide. I just added steps that way, you know exactly the things that are happening within each of the instructions. The from instruction is there, the run instruction is there, yum when we want to install SQL Server, and then the mkdir and so on and so forth. This is the Docker file for building a SQL Server on, in this case, CentOS 7.6.1810 image. Okay, and I want to, you know, lean and with minimal footprint. Unlike the Microsoft image, I don't want anything in here other than the SQL Server executable or binary. Okay, let's build a SQL Server on Linux image using CentOS, and because we're not passing any parameter on the installation, it's going to install the latest cumulative update. Let's use the Docker build command for this. -t, I'm going to tag this particular image, name it SQL 2017 CentOS :1.0, because I want to keep track of what version this is from my build. And run it. We will look at the different lines that the Docker build command would throw into the terminal or display in the terminal. You see step 1 of 8, it's running the from instruction. Step 2 of 8, it's pulling the repo file. Step 3 of 8, it's installing SQL Server. And this is exactly how things would look like if you're installing SQL Server on Linux. Like, pulling the binaries from the Microsoft package repository, and now it's updating some of the dependencies that SQL Server needs, and so on and so forth. Like I said, if you've installed SQL Server on Linux, this looks very familiar. And it's done. If you look at the steps 4 of 8, step 5 of 8, every step here represents the instructions in the Docker file. Let's have a look at the image that we just built. If you look at the size, it's 1.29 gig versus 1.4, the one that Microsoft built using Ubuntu 16.04. Now, of course, slight difference, but the real difference between the custom image that I built versus the one that was from the Microsoft public registry is the fact that the one that came from Microsoft has other tools in here like SQL CMD, ODBC, and all of the other stuff that Microsoft included. Like I said, I want my, not just container images, but my deployments to be as lean as I possibly can with minimal footprint. And that's the reason why you got like 1.25 or 29 gig versus 1.4. Let's run this container or a new container based on this image. First, let's stop our existing container, the first one that we created. Why I want to reuse port 1433, I don't want to be using other port number. because I don't want to have that conversation with network administrators and request for firewall exemptions for specific port numbers. I just want to use the same port number 1433. So I'm going to stop this particular container. Now that this container is stopped, I can now create a new container based on the custom image that we just created. And I'm going to use this command. Now, this command is similar to the one that we used, except, of course, well, we're using a much shorter name. We don't have the mcr.microsoft.com because we tagged it the name that we provided when we built the custom image. I'm going to run this. And there you go. Up and running. Okay. Of course, I would have to wait for a few more seconds until the entire upgrade process completes before I can connect to it. But let's assume that it's already there. Let's connect to the database using SQL Server Management Studio. Now I'm going to open a new query window, run the exact same queries. Now keep in mind, this was the results of the query from the one that we pulled from the Microsoft Container Registry. This one is from the custom SQL Server on Linux image that we just built. And look at the difference. This one is now running SQL Server 2017 with the latest CU, in this case CU22, running on CentOS Linux 7. This is what we provided in the from instruction. And of course, the host name that we provided is Linux SQL 02 compared to the Linux SQL 01 that we had earlier. This was the one from the Microsoft Container Registry that we pulled, and this one is from the custom SQL Server on Linux image that we built using CentOS. Now, if you want to build your own, let's say Ubuntu, we can explore that. I have another folder here named Ubuntu. And if we explore the Docker file, looks exactly like what we saw on the slide, with, again, some additional comments, step 1A, step 1B, and so on and so forth. But this is exactly what you saw on the slide. The way that you install SQL Server on Ubuntu is different from installing it on a Red Hat Enterprise Linux or a CentOS Linux. These are all outlined in the Microsoft documentation. But again, the point that I'm trying to make is I simply use the different commands for installing SQL Server on Linux, use those as definitions inside a Docker file to build my custom SQL Server on Linux image. Let's build a SQL Server on Ubuntu Docker image based on this Docker file. And because we're not passing any parameter for the installation, this is also going to be installing SQL Server 2017 with CU22, the latest one. So let's build. Let's let me clear the screen first and build this one using a different name. Similar to what you saw earlier, every step here represents a line, or not a line, but an instruction inside a Docker file. And there it is. We built a custom SQL Server on Ubuntu Linux image using a Docker file. Let's have a look at the size. It's a little bit bigger than CentOS, 1.33 versus 1.29. It's still smaller than the one that came from Microsoft. Let's now build, or rather create or run a new container based on this image. But I'm also going to stop the existing one. Because I simply just want to reuse the port numbers for connecting this new container. I want to stop that, and I'm going to create a new container based on that. I'm going to name it Linux SQL 03. Same parameters as the previous containers that we've created, except this one will be based on the SQL 2017 Ubuntu custom image that we just created. So let's use SQL Server Management Studio to connect to these this particular instance inside a container. I'm going to use the exact same queries. And there you go. We're running a new SQL Server on, in this case, Ubuntu container based on the custom image that we just built. We named it Linux SQL 03. We've got SQL Server 2017 with CU22. So I just showed you how you can create your own custom SQL Server on container images using a Docker file. And you can go crazy with this if you want, depending on how you want to incorporate this in your deployment practices. The important thing here is you know how to use the Docker file, how to write instructions in a Docker file to build your own custom SQL Server on Linux images or even Windows. I want to really just quickly show you how a Docker file looks like for Windows. I'm not going to build it because it will take forever to build it. In this case, I have a folder named inside a C drive named Docker build. But unlike installing SQL Server on Linux, when you install SQL Server on Windows, which you're pretty sure you're aware of, you need to have the installation media accessible to you. Unlike, pulling from the internet and installing from there. So in this case, what I did was to copy the entire installation media in this subdirectory SQL 2016 dev_sp2. Now let's have a look at the Windows version of the Docker file. I'm going to use the get content PowerShell commandlet for this. And similar to the Docker files for Linux, this is exactly what you saw on the slide with, again, some comments on the different steps. But basically, this is, how the whole Docker file looks like. And it's the same way that we build our custom SQL Server on Linux images. We use the Docker build command inside a Windows Docker host to build a custom SQL Server on Windows image. To sum it all up, I just want you to really think about containers and DevOps. Like I said, DevOps is an entire framework and a practice in and of itself, which is a combination of all those four components that I mentioned earlier in the presentation. And DevOps is just one of the tools available to make DevOps a little bit easier for you. You really have to consider all of those different components like automation and cultural philosophies and adding tool sets in the mix. We're barely scratching the surface here. If you want to dive deeper, I've written a series of articles at msqltips.com so that you can, not just watch the recording after the conference, but also to try it out on your own. In the series of articles, I've written how to run containers, how to pull images from the Docker Hub, how to build your own custom SQL Server on both Windows and Linux images. And there are examples, sample code, sample Docker files that you could also modify to suit your need. If you want to dig even deeper, I highly suggest that you get a copy of my book, The SQL Server DBA's Guide to Docker Containers, where in one of the chapters where I got from for this particular presentation, I even showed you how you can create a custom Docker file where you can run bash scripts that would include potentially creating a user database or running a T-SQL statement to create a database schema and stuff like that. Because you can really go crazy with creating your custom SQL Server on container images to meet your specific business need. And with that, thanks for attending my session. I hope you enjoyed the remainder of the conference.